Hello, and welcome to Astronomy 100. In the previous segment, we saw how when elements are excited, they give off light, and the colors that they give off can be interpreted through a prism, which will, of course, show you the lines that they produce. And what we also saw was how Bunsen and Kirchhoff made the discovery that the different patterns of lines that you see through various chemicals are unique to that element, so that any particular element has a pattern of lines that's unique to just that particular element. And then we saw how Kirchhoff was able to explore the idea of how spectra are produced. And if you recall, there are basically three types of spectra that can happen as the result of the situation. So let's go to our first picture to remind ourselves where we left off. If you recall, Kirchhoff discovers that under one condition you can get a continuous spectrum where all the colors are present, no colors are missing. Under a different condition you can get what's called an absorption line spectrum. In this case you have a colorful background with certain dark lines in places where colors are missing. And then the third situation is called an emission line spectrum, where essentially you have a dark background but only certain colored lines present. Now, the one thing that Kirchhoff could not do was explain the physics of why this is happening. And the reason why he couldn't do that is because the physics of the middle of the 19th century just had not progressed far enough in our understanding of how this works. And primarily this is because the physics of spectral lines involves the behavior of the atom. And so what we're going to talk about in this segment is how the atom behaves and what the atom is doing inside that will cause these lines to occur. But what we need to first start with is a basic overview of what atoms are. So let's go to that. What we now know is that the elements of our universe are composed of little tiny particles. And if you want to think of a definition of what an atom is the smallest increment of a particular type of material that still retains all of the properties of that material. So you can divide something into smaller and smaller pieces, but eventually you get to a point where you have the smallest possible piece of something and it still retains the property of what that particular substance is. So all atoms have various basic properties to them that they share in common. And let's start with the components of the atom. What you can see in this picture here is that inside of every atom there is the central portion called the nucleus. And the nucleus is composed of two different types of particles. One of the particles is called a neutron. The other particle is called a proton. So protons and neutrons make up the nucleus of every atom. Surrounding the nucleus of the atom are the electrons, the realm of the electrons, and these particles will move in orbit around the nucleus. So sometimes you will hear them referred to as electron orbit levels or electron shells, but any electron goes around the nucleus, around and around and around. It is very similar to a planet orbiting around the sun, but it's not the same physics, but it's just very similar in the way that it behaves. So the nucleus is where the protons and neutrons are. The electrons will orbit around the nucleus. Now, it is the electrons that are the important part of this, and we'll come back to them in just a minute. But let's start with a couple of basic ideas that are related to all materials of our universe, all elements of the universe. And to understand that, we need to move to the periodic table of the elements. Now, remember, this is not a chemistry class, but a couple of ideas to remind you of where this is coming from. The periodic table of the elements is essentially all of the elements that our universe naturally is composed of. And there are 92 naturally occurring elements in our universe. And the organization of this table into the periodic table of those elements basically arranges the various elements of our universe into certain places on this table based on their behavior and, of course, how they relate to other elements. And again, we'll leave the rest of that for a chemistry class. But an example is, here is the element hydrogen, and then we go all the way across over here. This is the element helium, and then we come all the way back across over here, and then we get to lithium and beryllium and so forth. Now, the periodic table of the elements lists all of the 92 naturally occurring elements, and you'll notice that if we go all the way down to number 92, this is the element uranium. You'll notice there's a number in the top of each of these boxes, and this number is called the atomic number. Now that's a very critical number to know, and you'll notice that the first one we have over here, hydrogen, is atomic number 1, and then all the way over here, helium is atomic number 2, lithium is atomic number 3, and so forth. Now the atomic number represents the number of protons that are contained within the nucleus of the atom. So if atomic number 1, being hydrogen, is number 1, it's because there is 1 proton in the nucleus. And helium is atomic number 2 because there are 2 protons in the nucleus. And then lithium has 3, and so forth. So element number 92, uranium, has 92 protons in the nucleus. The nucleus also has neutrons, but the atomic number represents the number of protons in the nucleus. Now, to show you an example, let's start with hydrogen over here. If we were to kind of zoom in and look at a hydrogen atom, we would find the 1 proton in the nucleus, and then surrounding the nucleus would be the electron in an orbit. And so this electron is going around and around. If we could animate this, we would see this going around and around the nucleus. Over here, atomic number 2, which is helium, has 2 protons in the nucleus. It also happens to have two neutrons, but you'll notice that it also has 2 electrons that circle around the nucleus. So element number 2, 2 protons, element number 1, 1 proton, and the appropriate number of electrons to go with it. So keep in mind, all 92 elements have a different number of protons that you find in the nucleus. And we'll find out in a minute why that's going to be, of course, very important. So what we're going to do is we're going to talk about the rules that atoms live by. It's as if there is programming that makes atoms do what they do in our universe. And these rules can be sometimes quite interesting, shall we say, quite exotic, maybe not necessarily something that's related to your everyday life. So they're a little bit strange. But what we're going to do is run down the rules that basically govern what it is we see when we see emission lines, or govern what we see when we see absorption lines. So let's start to take a look at some of these rules. Here's the first one. If on the right here is our atom, and we're going to make it very simple, we're going to use a hydrogen atom, actually for 2 reasons. Hydrogen is the most abundant element in the entire universe. So in other words, there's more hydrogen in our universe than anything else. And secondly, hydrogen is a very simplistic atom. It has 1 proton in the nucleus, and it has no neutrons if it's in the normal form that we find it in our universe. So we're going to use a hydrogen atom to make life simple. The rule number 1 that we're going to talk about is that inside of every atom, there are certain distances away from the nucleus that the electrons are allowed to orbit. So we're going to label them with numbers. This is what we would say is electron orbit number 1. And then at this distance, this is electron orbit number 2. And then this distance would be electron orbit 3, electron orbit 4, and so forth. So there are predetermined distances that the electron is allowed to be in. And so think of it as, even though you'll notice there's no electrons in this picture, these are the distances ahead of time that are determined for where the electron is allowed to be. So only certain distances are allowed by each atom. Strangely enough, that means that you can't have distances in between that are allowed. Distance 1 is allowed, distance 2 is allowed, 3 is allowed, and 4 is allowed. But the electron, of course, has to be only where it's allowed to be. And that kind of brings us to rule number 2. Rule number 2 is that electrons can orbit only in these allowed orbit levels. So if this hydrogen atom allows these specific levels for hydrogen's electrons to be in, the electron has to be only where it's allowed. So the electron can orbit around in this level, it can orbit in this level, it can orbit in this one or this one, but it cannot orbit in between. So in other words, if we tried to make the electron orbit where there's not an allowed level, the electron won't do it. So the electron has certain levels it's allowed to be in, and the electron can only be in those allowed levels. Now the next idea is related to that. And so if we were to look at hydrogen, the element hydrogen, as opposed to the element helium, what you would notice is that the electron orbit levels are different. So notice that with hydrogen with its 1 proton, here are the orbital levels that hydrogen allows. And with helium with its 2 protons, these are the orbital levels that it allows. Notice how the distances for each of these orbit levels is different compared to the allowed orbit levels for hydrogen. So hydrogen allows these levels, helium allows these levels. So the question is, why are they different? The answer is that when you change the number of protons in the nucleus, it changes the number of allowed levels. So the fact that we have only 1 proton means you have these allowed levels, and when you change it to 2 protons in the nucleus, it changes the orbit distances. Notice it completely rearranges where the electron's allowed to be. So the number of protons in the nucleus determine what levels are allowed. And so every single one of the elements of the periodic table has a different number of protons and consequently a different set of levels that it allows its electrons to be in. So that's an important point that you'll see we'll come back to in just a second. Now the next rule is that if the electron is going to be in a level, it will have an energy associated with it. So each one of these levels has a certain amount of energy associated with it, and the way that it works is the level that is closest to the nucleus of the atom is the lowest energy level, and when you switch to another level and you get further away from the nucleus, it's a higher energy level, and then a higher energy level, and so forth and so on. So when you're close to the nucleus, the levels have low energy, but then higher energy, and higher energy. The highest energy level is furthest away, the lowest energy level is closest to the nucleus. Now, if an electron has a certain amount of energy associated with each level, it also means that there is going to be a maximum of the energy levels. In other words, there's not an infinite number of levels that an atom can have. There's a limit to how many it can have. Now, the next set of rules has to do with the behavior of the atom, and it's an important rule. This particular rule says that atoms prefer to be in the lowest energy state. You notice I have the word prefer in quotes because atoms are not actually alive and they don't think and feel, but if an atom is given the opportunity, it will always keep the electron in the lowest energy level possible. What that means is if I were to take this electron and force it to go up to level 2, the atom will automatically bring it back down to level 1 if given the chance. So anytime the electron is raised to a higher level, the atom always tries to bring it back down to the lowest energy state. Now the last set of rules govern how the electron can change levels. What you'll notice in our animation here is the electron is going from level 1 to level 2, and then it comes back to level 1, and then this whole thing starts all over again. Here's what's happening. Because each orbital level has a certain amount of energy associated with it, what that means is that if the electron's going to be in a particular orbit level, it has to have the energy required by that level. So if I'm going to make the electron go from a low energy level to a high energy level, the electron has to change its energy. It has to go from a lower energy state to a higher energy state. Well, how can the electron gain energy to jump to a higher level? One way that it can do that is if the energy that comes into the atom is in the form of a photon, remember a photon is a carrier of energy, then the electron will gain the energy, jump to a higher level. So you can give an electron energy by giving it a photon. The photon causes the electron to gain energy, the electron jumps to a higher energy level. But this is where the previous rule kicks in. What you'll notice is once the electron's in the higher energy level, the electron's going to be brought back to the low energy level. So the photon comes in, forces the electron to a higher energy level, but then the atom immediately pulls it back down to the lowest energy possible. So the energy of the photon forces the electron to a higher level, but then the atom automatically tries to pull it back to a lower energy level. So even though you keep trying to force it to a higher level, the atom will always bring it back. So These are the basic rules that are governing the inner workings of the atoms. And what we're going to do is see how all of these basic rules can come together and force the atom to have a behavior that will cause it to have either a dark line profile against bright colors or a bright line profile against dark background. And we'll see how all of this is related to the emission line spectra, absorption line spectra, and of course, it's the internal workings of the atom. So we'll see you in the next segment. We're just about out of time for this one. I hope you'll join me.